What's up, everybody? In this video, we're going to cover USACO's 2022 February contest at the bronze level, problem number 3, blocks. In an effort to improve her vocabulary, Bessie the cow has obtained a set of 4 wooden blocks, each one a cube with a letter of the alphabet written on each of its 6 sides. She is learning how to spell by arranging the blocks in a row so that the letters on top of the blocks spell words. Given the letters on each of Bessie's 4 blocks and a list of the words she would like to spell, please determine which of the words on her list she will be able to spell successfully using the blocks. Okay, so Bessie's got these blocks. There we go. Each block has letters on each of the faces. And we've got 4 of them, 1, 2, 3, 4. And we have to figure out whether or not we can spell the words that Bessie wants to spell. So for example, Bessie might have the word cow. And then we would try to see if there's a way to spell that using the blocks that we have. As far as the number of options we have here, for the first letter right here, we have 4 blocks to choose from. For the second letter, we have 3 blocks to choose from. For the third letter, we have 2 blocks to choose from, and then the last block wouldn't be a choice. It would just be whatever the last block is. So as far as the number of combinations we've got 4 choices for the block for the first one, 3 for the second one, 2 for the first one. We can multiply all that together. And that gives us 24. So 24 is the number of arrangements of the blocks that we have. There are 24 possible orderings we could put the blocks in. If we wanted to list them all out, it'd be something like 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 2, 1, 3, 4, and so forth. There's 24 of these. Additionally, with each one of these blocks, you have 6 choices on each of the faces. So on a 4-letter word, that's going to be 6 times 6 times 6 times 6. So let's have a look real quick. 6 to the 4th power. 4th power is 1,296. We multiply that by 24, which is the number of orderings. We've got 31,104 possible, basically possible words we could make. 31,104. I'm gonna write that down. 31,104. Okay. So if I've got 31,104 words I could possibly form, it looks like the number of words that we might have to spell is up to 10 words at most. The first line contains N, which is 1 through 10, the number of words that Bessie would like to spell. The next 4 lines each contain a string with 6 uppercase letters representing the letters on the 6 sides of one of Bessie's blocks. So that's these 4 dice right here. There's always 4 of them. And then the next N lines, which is whatever this is, that many lines, contains the N words Bessie would like to spell. Each of these is between 1 and 4 uppercase letters long. For each word on Bessie's list, output yes if she's able to spell it using blocks and no otherwise. So there's no fancy techniques happening in here. This is mostly a bookkeeping sort of problem. There's 2 ways you can approach this problem. I've written the code for both of them and they both pass the test cases, all the test cases. So you can use either approach you want. This is a good excuse to work on sets. So if you aren't so familiar with sets, I would recommend trying to solve it using that. But basically, here are your 2 options for approaching this. The first option, which is the most efficient one and is the one that is stated in the official solution, is to generate every possible word you can. In order to generate every possible word you can, basically what you're going to do is you've got your 4 blocks. I'm just going to kind of draw little pictures of blocks here. 1, 2, 3, 4. So this is the mu block. This is the u block. This is the A, B, C, D, E, F, D block or whatever, and then this is the U block. If we use these 4 blocks as an example. So what you need to do is try to generate every possible ordering of these blocks. One way you could do that would be very easy would be to have a for loop for I from 0 to 4, for J from 0 to 4, for K from 0 to 4, and for KL. I don't usually use L in a for loop, but for L from 0 to 4. So once you have these 4 loops, then if you can ensure that I is not equal to J, and also I is not equal to K, and also I is not equal to, that's an I is not equal to L, and J is not equal to K, and J is not equal to L, and K is not equal to L. It's a lot of those, but basically ensuring that all those values are different from each other. If you ensure all those values are different from each other, then this is a brute force solution that's going to give you every possible block ordering. 4 times 4 times 4 times 4 is going to be, what is that, 16, 64, 256. There are 256 iterations that are going to happen on this innermost loop. But if you use this if statement, only 24 of them are going to be valid because most of those orderings are going to involve duplicates. For example, if you have 0, 1, 2, 0, that's not valid. If you have 1, 2, 3, 1, that's not valid. Most of the orderings are not valid. If you were clever about it, and you can come up with a clever way to do permutation, so you can save a lot of these iterations. But again, this isn't that big of a problem. We don't have that many words, and the blocks are all kind of a set size. So if you want to just have a for loop, 4 for loops in each other, and then just make sure that all the values are different, that's a quick way to do it. One thing we can't do though is we can't have like j equals I plus 1 to try and save iterations, because we do need to try every order. We have to try 1, 2 as well as 2, 1. So starting with j being larger than I isn't going to give us that. So that's going to be on your outside. On your outside loop, essentially what you're doing is you're assigning different numbers to each block. For example, 2, 3, 1, and then 4. Or if we do 0 indexing, it would be 1, 2, 0, 3, or whatever. But basically, you're assigning numbers to all the blocks, making sure they're all different. Once that's done, now we've got an ordering for the blocks. So this has the A block as the first one, A, B, C, D, E, F. This has the M block for the second one, that's the mu block. This has the O block, the all O's, and then the U, W, X, Y, Z block is the last block. Once you develop that ordering, then for each of those blocks, you've got 6 sides. Again, we can just do a bunch of for loops. For, we're on LM, for M from 0 to 6, for N from 0 to 6, for O from 0 to 6, for P from 0 to 6. And then each one of these represents what letter you want off of each block. So M is like whatever face letter you want off the first block. N would be whatever you want off the second block. O would be whatever you want off the third block. And P would be whatever you want off the fourth block. Now, once we've done all of this, essentially we've got our blocks here. We need to have these in some sort of a data structure where, given some letter I, we can select one of those blocks. So you have like blocks, square bracket I, to select which block you want. And then square bracket, what were we on, M, to select which face you want. So as this goes 0, and then 1, 2, 3, whatever, that's going to be picking different blocks, the M block, the O block, the A block, and the U block. Likewise with the M, as that goes 0, 1, 2, 3, 4, 5, 6, that'll be selecting the first letter, the second letter, actually we go to 6, third letter, fourth letter, fifth letter, and sixth letter. So what to do with this information once you have it? You've got 2 approaches. And again, the most efficient solution is going to be to have a set of strings. So what you do is you develop your set of strings. And then every time you run through this loop, you're picking a unique ordering of blocks and a unique combination of faces. Once you get that word, you stick that into the set. And you can just brute force it out, and then you can add every possible word that could be made with the blocks to the set. And again, I think we figured out there's like 31,000 words. So there's not going to be that many words, and there's probably going to be some repeats. For example, you see that these are all O's. In the real world, we've got 6, 12, 18, 24. We've only got 24 faces. So technically you could have the entire alphabet represented and there would be no repeats. So we'll just assume that there won't necessarily be any repeats. But even if that's the case, at most 31,000 words. From there, reading these words and seeing whether or not they're in the set, that's going to, depending on your base language, happen in pretty much in constant time. If you're in C++, remember to use an unordered set. And I have a video that describes that if you're not familiar with those. The unordered set will give you a constant time lookup instead of a logarithmic time lookup, which will speed up your code a lot. It does come at some trade-offs, and I go into the details on unordered sets versus classic sets in the video. But basically in the original, when they originally solidified the current version of C++, I believe they used the red-black tree for the set. That's what's in the official standard. So the unordered set will give you faster lookups. So that's your first option. So just to kind of recap that option, you have a for loop for I that goes from 0 to 4 to pick which block you pick for the first block, 0, 1, 2, 3, 4. Then J to pick the second block, K to pick the third block, L to pick the fourth block. Make sure that I is not equal to J, which is not equal to K, which is not equal to L. And you do have to nest these. Just because I is different from J and J is different from K and K is different from L doesn't mean they're all different, because this could be 0, 1, 0, 1. And then that's not valid. They have to all be different numbers. There's again, that's going to be probably the easiest way to do this. Once you verify that they're all unique, we have M, N, O, and P, each going from 0 to 6, picking which face you want off each block. And then you can just use your blocks, square bracket I, square bracket M for the first letter, plus blocks, square bracket J, square bracket N for the second letter, and so forth. One thing to watch out for is you do need to allow for 1, 2, 3, and 4-letter words. So not all of these are going to be 4-letter words. When you're building the set, one of the words will just be block IM, and that'd be it. One of them will be block IM plus block BJN. One of them will be block IN plus JN plus KM or KO or whatever. You get the idea. So building every possible 1-letter, 2-letter, and 3-letter and 4-letter word from those combinations, putting them all in the set, and then as you iterate through these, just check to see whether or not they're in the set. Now, there's one other way to do this that doesn't require a set, which I fiddled around with, and it does pass all the test cases. The setup is very similar. You have for each of these blocks, you read these in, and then as you're reading the word, essentially what you're doing for each letter, C-O-W, you're picking which of the 4 blocks potentially could have that letter, which of the 4 has this letter, which of the 4 has this letter. And again, trying every combination. So the 4 loops are still going to have I1 to 4, J1 to 4, K1 to 4, L1 to 4. But once you pick those blocks, rather than generating all the words, you check to see, does block whatever I is have the letter C? Does block J have the letter O? Does block K have the letter W? So for example, when I is 0, and then, oops, let me write an I here. So when I is at 0 and J is here and K is here, for example, as you're looping through, you check to see, okay, I'm trying to spell C-O-W. Does this string contain a C? Does this string contain an O? Does this string contain a W? And if all 3 of those are true, that means the word is spellable. Now, what this means is that for every one of these words, you're going to have to go through 31,000, whatever it was, 104 iterations. Because you have potentially 10 words, you're going to have 311,000 iterations, which actually, this is still a very small number from a programming standpoint. So that's your other option. And just kind of to recap that, for each one of these words, like move, M-O-V-E, essentially you have block 0 for the first one to start off with, block 1, block 2, block 3 is going to be your first combination. We check to see, okay, is there an M on the first block? Is there an O on the second block? Is there a V on the third block? Oh, there's no V on the third block. So we would go to the next combination. The for loop will spin around a little bit, and then you'll have 1, 2, 3, 1, 0, 1, 3, 2. Same process is going to repeat. We check to see, is there an M on the first block? If you're clever, you can keep it from rechecking that. O on the second block, V on the fourth block, and then E on the third block. That turns out to be true, and that shows you that the word move can be spelled. So those are your 2 options. First option, go through every possible ordering of the blocks. For each of those blocks, go through every possible face that you could choose, combine those into every possible words and put them in a set, and then go through each of the words and check to see if they're in the set. The other option would be to load all your blocks and store them in some sort of probably a 2D array would be the easiest thing to do. Then go through each word. For each word, try assigning a different block to each letter and see whether or not that letter is on the block. And if you're able to find an arrangement of blocks where all the letters can be found, then that means that word's spellable. You print out a yes, and then you move on to the next word. So that's how to solve this problem. Good luck coding it. Now we'll talk to you on the next one.